Hello, hello everyone. Am I audible? Okay, thank you. So let's wait for 1 minute more. And if people are joined, then we can start. Okay, so let's start. So myself, Suluto Samanto. So I am your teaching assistant for this thermal physics course taken by Professor Demal Banerjee this semester at NPTEL. So before starting the discussions, okay, so I would like to talk about briefly myself. And I am a first year PhD student at IIT Kanpur in the Department of Physics. So I study a wide range of theoretical aspect of high energy physics. So my research is focused on mainly on exploring physics beyond the standard model. So standard model it is the most accepted theory of elementary particle physics. Okay, so but there are several limitations. That's why we extend the beyond standard model things. So the Ministry of Human Resource Development, Government of India financially supports my research and under the Prime Minister Research Fellowship Scheme. So that's all. And now come to the main point. So hope you guys, 1 minute. Hope you guys are watching the lecture weekly and enjoying it. So this live session is mainly it's repeated weekly at this time. So every Saturday, let's say 4 to 6 p.m. And the main purpose of this conducting this live sessions to solve various problem and that's your help to solving the weekly assignments problem and clear your doubts related to the week contents, etc. So hopefully in the ends you guys are familiar with the subjects and understand the basic concepts. Okay, so all these sessions will be recorded and share with you all, and which will be helpful for those who are not coming. There are okay, 1 minute. Yeah, so there are several internet issue or any other problems. So I strongly suggest you participate the course discussions forum and post your queries, okay, etc. And we will answer these questions, or otherwise we discuss this live series the questions. Okay. So let us start without any further delay. So I will like to revisit some very basic concept related to the weak contents when we solving these problems and discuss some more advanced things if time permits. Okay, and some tricks to solve these problems, etc. Okay, so that's just revisit your weak content and the solving the problem. Both are do simultaneously. Okay. So yeah. So any questions that I will have in the weak content, or otherwise we discuss the assignment problems. I think the most of the questions that asked in the forum is answered, but there are some questions. Yeah, so one thing, yeah. So equipartition energy problem. So these questions is not answered. That the question is that Somiron Odhikari asks, and the question is that in equipartitions of energy, half kT, is it total energy or kinetic energy? What happens if car moving with a cylinder? These types of questions. So equipartition energy is very specific prompts that just a minute. Okay, so let's share the screen. Okay, and share my screen. Yeah, so start sharing. Yeah, so my screen is visible now. Hello. Anyone can say that my screen is visible or not? Okay. Okay, so the questions is asked that equiperson's energy half kT is total energy or kinetic energy. So there is no specific form of the total energy or kinetic energy. It's energy that is half kT to every mode of degree freedom. Okay, so there is a suppose f mode of degree of freedoms. Okay, so then the equiperson energy tells that f by 2 kBT. Right, so this is actually part of total energy. So if you separately calculate, let's say, kinetic energy and potential energy, so in kinetic theory there is no potential energy, right? So the gas are move freely and all are the kinetic energy. So in this case you can tell that the kinetic energy from f by 2 kBT. But when you describe the interacting system types things, okay, so I'm already tell in the on questions in the discussion. Okay, and then the potential energy also contributes. So it actually part of this. Okay, so part of kinetic energy and part of potential energy are two separately, but in this case there is a no potential energy, so all the things are kinetic energy. So you can say total energy or you can call kinetic energy same things. Okay, so it's clear. Any questions further? Hello. Okay, I think it's clear now. So that is E total. Okay. So now the other questions I have not answered in this seasons. There is a most probable speed. So is it most probably going to 1 over root b? Yeah, so most probable speed, how to calculate? Let's say your distributions f is what is the distributions? The second problem, f is, let's say, distribute v square e to the power minus v square by kbt or 2 kbt mv square. Let's say call that the alpha v square. Okay, so there is a some factor a is the normalization factor. So now we calculate the most probable speed. That means f is a function of v. So let it clearly, f is a function of v, and then so just we calculate that df of v by dv, df of v by dv. Just a minute. Yeah. Okay, so df by dv equals to 0 at v equals to, let's say, v mp. Okay, the most probable speed. So then we can calculate just v mp from this, and you get the one derivations, and you get, let's say, 2 kbt by m. Now in this case, let's say alpha, if what is b, I don't know that what is b is. Let's check the, oh, so this is b, right? So if this alpha actually b, so then you say that this b, what is the values of b is m by kbt, right? 2 kbt. So in this case vmp is 1 over root b. That is right. Yeah, there is a mistake. So in the notes I think there is a typo, so this is actually 1 over root b. Okay, so it's now clear. Just to calculate this derivative, I think you are guys familiar with this derivation. So the simple derivative, and put v equals to vmp, and I get vmp. Yeah, so now it's clear, right? Any questions from this? Hello. Okay, so I think it's now clear. Okay, so go to the next problem. One more questions. Okay, so then Okay. So I think other questions I have already answered, and one more thing, the advanced. Can you, sir? Can you explain what a advanced postulates of kinetic theory of gases? Purushottam asked this question. So there is a no advanced postulate. So we can, the kinetic theory of gases is not. We can tell is different way, right? So that you can explain it differently. There is no advanced postulate. I think the set cannot tell this time types of advanced postulates. Okay, these types of word, but yeah. So there is no advanced postulate. So the postulate is same, but the way some books are represented in different way and some books are represented in different way. So in these things, but the postulate meaning is the same. Okay, so I think there is no advanced postulate type of things. Okay, so this question is that, and yeah. So one more thing I have to discuss. I like to discuss that. Yeah, so the last point of this basic postulates of the KTG is the kinetic theory of gases. They say that the gravity, right? So gravitational interactions are attractions of molecules are negligible compared to other interactions. So what can other interactions be? So this is a very good question. That okay. So first of all, we say that the interactions. Okay, so how we describe this interaction? So interactions are describes the describe. Okay, so 1 minute. I think some people can show. Okay. Okay, so the interactions are basically described by the potentials. Okay, so if you have a interactions, then there is some attractive potentials or repulsive potentials. Yeah, any question? Hello. If in not any questions, then please unmute yourself. Any questions, Archana? Hello. Okay. So then, okay, so interactions are basically described by the potentials between the molecules. Okay, so in kinetic theory of gases, we can treat that the molecules are freely move. Okay, randomly movement. So there is no potentials. Okay, we cannot just a minute. So we cannot describe assignment two problems. Solve set classes. Assignment two problems. Yeah, so I mainly describe the assignment 2 related problems. So if you solve the assignment 2 problems, then we can discuss more things. Okay, so that is depends on you guys, what you guys want. Okay, so I think I go into this problem very roughly. Okay, so if you have any doubts, so you can ask. Okay, so that is the question, that the interactions can be described by the potential between the molecules. So in postulates of kinetic theory of gas, we treat that the molecules are freely or randomly movement, right? So there is no potentials. So there is only kinetic energy, right? So there is no potentials and only kinetic energy. So that's why we say that but still there is a gravitational attraction energy, because the gas molecules are massive, right? So there is a mass of gas molecules. So due to this mass, there is a gravitational potential energy. So this cannot be removed, right? So this gravitational potential energy you can neglect with respect to your kinetic energy, right? So your, because the random movement of the particles, there is a kinetic energy too large rather than the gravitational potential energy. So gravitational potential energy in this context we neglect. Suppose we have a system, there is a attractive systems. In more real systems, there is a more real gas, so there is a attractive potential rather than the gravitational potential, rather than any kind of other potential. So other potentials means the attractive potential, and but still there is a gravitational potential. But in this that case also, the attractive potential with respect to the gravitational potentials are continued. Okay, dominant continuous. So the gravitational potential is always neglected in real system, and it's a very good assumptions to cancel the gravitational potential energy. So that's things I have already written in the discussions forum, but I just explaining for that. Any questions or any, yeah, so any questions anyone can I think hope all it's clear. So if any questions, please ask. Yeah, it's clear now. What is other interactions on what is why we can neglect the gravitational potential energy? Hello. Okay, it is clear now. Or any other questions? Okay, so now go to the assignment problems and related some basic things I have to discuss. Okay. Yeah. So first, I would like to discuss that how to convert mole to gram. Okay. So let's say, so what is the definition of mole? Can anyone tell that what is the definition of mole? Hello. Yeah, so why 12 gram of carbon? So okay, so discuss it. So let's say one, you see that the 1 mole of carbon equals to 1 mole of molecules, so it's related to the 12 carbon carbon. So what is the atomic weight of carbon? So atomic mass. Okay, so atomic weight of carbon, yeah, 12. So that means that what is the mass of this? 12 in units. Can you tell the units of this thing? Just to say that 12. What is the unit? It's gram. Yeah, that's good. That AMU, right? So now we convert this AMU to gram. So that means one carbon 12, one C12. So that's why 12 AMU. Now 1 mole of carbon, that means Na, Avogadro number of carbons, right? So that means Na into 12 AMU. Now you say that you know that the 1 AMU equals to 1 by Na gram, right? So then just Na and 12 by Na gram. So that means 12 gram, right? So that's why you say that the 12 gram of carbon, that means a 1 mole. Okay. And 1 gram of hydrogen, that's in the 1 mole. So similarly, let's calculate the ionic substance. Let's say 1 mole of NaCl. Can you calculate quickly for what is the how much gram for that? 1 mole of NaCl. So NaCl is ionic substance, right? So they form an ion, so Na plus and Cl minus. So we need a formula weights, right? Rather than the atomic weights. So the formula weights FW for Na, how much? 23, right? And formula weight of Cl 35, right? And then 1 mole, so that means the Na, so that's replace just gram. So as do it previously. So 23 gram plus 35 gram, right? So this 58 gram. So that means 1 mole of NaCl is equals to 58 gram. So there is a x mole of NaCl. It's just 58 of times x. So similarly, in the assignment there is a given in the NaOH. So just from that NaOH is Na plus OH minus and calculate the formula weight of NaOH and convert to the gram. Okay. So I think it's clear now. Any questions related to this? Okay, so now we go to the second things. Yeah, so second thing is that let's given a pressure, okay, and calculate and given a number density and calculate the temperatures. So yeah, so in kinetic theory of gas we only deal with the ideal gas. There is a no interaction. So the ideal gas equations, I think most of you know that the PV equals to, let's say, N kBT, right? So N which is the total number of molecule, B is the total volume, okay, and P pressure and T temperatures, and kB is the Boltzmann constants. Now we can write this P actually N by V kBT. So this N by V is the number density because the total number per volume, okay. So this is gives the number density. So this is given, let's say N is given and P is given, sorry, P is given, so we calculate T, right? So P by, let's say this is number density N kB. So kB is a Boltzmann constant. I think most of you know that the value of this 1/1.38 into 10 to the power, let's say, minus 23. What is the unit? Hello. So what is the unit of this Kelvin? Yeah, right, joule per Kelvin. So just calculate and we get the temperature T, right? So even proper unit. So N you can calculate in SI units because this you say the joule per Kelvin is a SI units, right? So then we can write written the N in terms of SI units and then calculates, okay. And pressure is also written in the SI units. So SI unit, SI unit, okay. Then you get this T some Kelvin. Okay, so I am not doing the exact calculations, so the way how to do the calculations, okay, so you know these things. And the one more thing, yeah, so now go to the third case, third problem. So can anyone tell me that what is the values of this P RMS velocity of this Maxwell-Boltzmann distributions? What is the formula of this? It's root of square root of 3 kBT by m. It is correct? Hello. So this is the RMS. The RMS velocity means the root mean square velocity of these free molecules, okay, in kinetic theory of gas. So we can, this formula comes from the Maxwell-Boltzmann equations, right? So Maxwell-Boltzmann distribution. So this formula is right or wrong? Can anyone tell me? Right. What is the M I am written? It's molar mass or what? Okay, so in the notes or in the lectures, you will see that the 3 RT by M, right? So this M actually the molar mass and this M actually the molecular mass. So if you multiply it by Na, 3 Na kBT by Na m, then you get that 3RT by M, right? So this is, so that means R is the thermodynamic gas constant. I think all of you know that, Na kb. So this is Avogadro number times Boltzmann constants. Okay, so then you say that this Vrms, actually let's say I want to know that this Vrms how vary with temperatures, right? So this Vrms actually the square root of temperatures, right? So if you increase the temperatures, then Vrms gases decrease, the RMS velocities of the gas molecules decrease, right? Then let's say you have a given, there are two temperatures, two substances, okay, one is temperature T1, another is temperature T2, and you calculate the RMS velocity of first to second. So Vrms 1 by Vrms 2, you get the of T1 by T2. So one is given, let's say T1 and T2, okay, and let this is 2 times of this, okay. So this ratio is given, let's say is 2, okay, this is given. So you calculate the T2 is 2 actually, T1 by 4, right? So this is the temperature relations. Now similarly we can change the mass. Let's say one molecule is heavy rather than, let's say, NH3 molecules. So we have calculated, say, NH3 molecules, V RMS velocity for NH3 molecule, and divided by V RMS, let's say H2, okay, and divided. So in this case the same temperature, right? So same T, we calculate these two different molecules, and so then it's inversely proportional to, so V RMS is inversely proportional to 1 over root M. This is only two variable, okay, one is T, one is M, 3R is fixed. So square root of T is proportional and 1 over square root of M is inversely proportional. So in this case it is, so then we can just divide it by this root of M H2 by M NH3. So now we write down the molar mass and we calculate this ratio, okay. So these things is now clear. Any questions? Hello. Okay, so now you can go to the next problems. Okay, so now calculate, let's say, the V average. So the average velocity. So average velocity, again we have said that 8 kbt by pi small n, right? So must remember that what is the small n and what is the capital N, okay. So when we write capital N, then we write then we must write the 8 RT by pi capital N, or you write in kbt, then you can write small n, okay, not capital N. So then again we calculate the same things, okay, and if you know that M, and if you know T, let's say T equals to 300 Kelvin at room temperature, you calculate, let's say, the average velocity of H2 molecule, right? So you calculate this, right? Just put in the form of what is the M and what is T, and kb is 6 and pi m, right? So what is the molecular mass of M2? H2. M of H2. Can anyone tell? This is the molar mass of H2. Hello? Two gram or yeah, so when you tell some number, that tell some unit, so otherwise there is a no. Why mole? Yeah, gram gram per mole, but we are considering 1 mole of gas. Okay, so because Na means that 1 mole. Okay, so yeah, so 6.023 into 10 to the power 23. This is mole inverse, right? So it's actually 2 gram per mole, but we are considering only 1 mole. So that's why yes, I multiplied that Na, right? So 8 Na kb, right? It's not 2 kb, 2 Na. So we multiplied 1 Na, that means 1 mole. So m, so then this is 2 RT by pi capital M. So m in this case 2 gram, right? Because we are considering 1 mole. So then 8 into, I think we will know that the RL value is 8.314, right? And let's say T is 300 and then pi M is 2. So now convert this gram to kg, right? Because 8.314 RL value is 8.314 is joule per mole per Kelvin, right? So if you consider 1 mole, then this mole already cancel, and then Kelvin and joule. So joule is the SI units, but this gram actually CGS unit, so we can convert this to into 10 to the power minus 3 kg, and then just put it. So it got let's say 1782.5. But if answer is just not match with your exact, you can choose the correct. It's the nearly close to that. Okay, so I think there is some answer is 1.777 something like that. So you can choose this if not exactly matched. Okay, so this is now clear. Now the third point is let's say compare, there are 3 speed. Okay, so one is RMS speed, Vrms, and other is V most probable and V average, or you can write V average. So I think you know that first to calculate this VMP at first point. Okay, yeah, so VMP is root over 2 kVt by M, and Vrms is root over 3 kVt by M, and V average is root over 8 kVt by pi M. So now we compare and get these types of relation, that VMP, V average, and V RMS. Right? So now okay, so first to draw this. So f of V, know that sum a v square into the power minus alpha v square. So once you draw this, so you get these types of graph, right? Because the v square is this, and e to the power minus v square like that. So then you can multiply these two things, we get these types of graph, right? So let's do it color. So this is your FP. So in this case, this is the most probable speed when FP is maximum. So FP versus P. So drawing. So this is your most probable speed, and this is your average speed, and this is your RMS speed. So this point VRMS, this is most probable, because most probable speed where this derivative is 0, right? It's the maximum point or minimum maximum points, right? So the first derivative is 0. So you calculate the second derivatives and you get the negatives, right? So that's why you show that it's a maximum points, not a minimum, because the first derivative is also for the minimum, right? So once you calculate the second derivative, and again we put this VMP, let's first check. Okay, so D2F and dV2 at V equals to the same VMP. Okay, you must get negative and cross check. Okay, so step homework. and it's saying that this is a negative. So this point is VMP, this point V average, this is PRS, right? So now, so this plot is for a fixed temperature, right? So let's say this for temperature at T. Now we vary the temperatures. How this plot vary? Okay. So in this case, the alpha and A all are depends on temperatures, right? So you get that alpha is actually 1 over root B. That means, sorry, alpha is actually m by 2 cavity. So this is depends on temperatures, and A is also, I think, what is the value of m? Yeah, so m by 2 kBT, the whole to the power 3 by 2. Yeah, this is right. Yeah, I think this is right. So then let's say we increase the temperature, say T1, and we plot to define temperatures this graph T1 and T2. So let's say this graph. Okay, this is, let's say, about T1 and this is T2. So which graph is which temperature is larger, T1 or T2? Hello. Yeah. So can anyone tell me at which temperature is larger, T1 or T2? Yeah, so any possible way to deal with this problem? Okay, so so first we focus on the peak. Okay, so what the maximum values are there? So this is your velocity axis. Okay, just a minute. Okay. Okay, so this is your velocity space. Let's say P1 and MP1, maximum velocity, maximum most probable speed 1, and PMP 2, right? So you know the formula that PMP, the most probable velocity, is log of 2 kBT by m, right? So this is proportional to square root of temperature, but when the temperature increase, the speed must be increased, right? Most probable velocity can be. So in this case, that you see that the VMP2 is greater than equals to VMP1. So this implies that this T2 must be greater than equals to T1. Must be greater than T1, not greater than equal. Yeah, so must be greater than T1. Any questions? Hello. It is clear or any question? Okay, so then I might ask that why these types of things is true. Why this is not happens? Let's say this is T2. This is also later. So why this is not true? Why this red curve is not true here? So it is purely clear with that this when increase the temperature that VAP shifted, right? But now the peak is increasing. Why this is not true? Can anyone tell me the reasons? Hello. Okay. So what is the values of this? So this is MP, right? Let's say this point. This is MP, VMP, and what is the values of this point? It's VMP, right? This is the function of velocity. So at this point, because this is VMP, so this point is f of VMP. So now you know FV is, let's say this is the FV, a v square e to the power minus alpha v square. So if put f of VMP at particular point of this velocity axis, we calculate, then a VMP square e to the power minus alpha VMP square. So now this alpha and VMP square are inversely related to each other, right? So VMP is root over 2 kVt by m and alpha is m by 2 kVt. So this is actually then a VMP square e to the power minus 1. So then we can tell that a is actually 1 over t to the power 3 by 2. 1 over t to the power 3 by 2. And VMP square is t to the power what is it? 1. Right. So that means it's sorry. So that means it's 1 over t to the power half. Right. So that means when we increase the t, the peak must be decreases. So the values of the functions at this point it must be decreases. So that's why this is not the case. So in this case the peak is increased. Okay. So it is understood or? Yeah, now it is clear. Hello. Any question so far? Hello, am I audible?
Yes, sir, understood.
Okay. So I think the velocity distributions part is almost over. There is no problem. I think all of the problems we now you answer these questions in the assignments. So now go to the next things. It's called degree of freedom. Sorry, just a minute. Okay. Yeah. So let's consider a linear triatomic molecules. Linear triatomic molecule. Yeah, so linear triatomic molecules. So that means the system which look like this. Right. So all molecules are in linear. Separated. Right. So how many degrees of freedom was there? At moderate temperatures. Okay, so moderate temperatures means that the room temperatures. Okay, so around 300 Kelvin, let's say. So at these temperatures, how many degrees of freedom are there? So, so at moderate temperature there is no vibrational modes, so only translational, right? So plus rotational, right? So in this case, how many translation modes is there? Okay, so let's say three translation modes, three, and rotational. Okay, so this is not rotate in this axis. Okay, the other two axes, let's say this is x axis, another two axes you can rotate this system. So this is 2. So this is 5. This is true. It's 5. Okay, so what is the degree of freedom for the diatomic molecules? For diatomic molecule, what is the degree of freedom? High. But in this case, it's also 5. It is right? So for diatomic molecules, it is not 5, it is actually 7. So the reason is that here it also contribute to the vibrational mode, right? So at moderate temperatures, because this molecule can vibrate. So when we deal with the four atom in a chain. So in this case, there are two. This atom can vibrate. Okay, or this molecule, this atom and this atom can vibrate. Okay, so we can allow this at moderate temperature also. Okay, but this case at moderate temperatures there is no vibration because two digits. Okay, but in the middles, if there is a atom or say one atom, in this case there is a two atom. Okay. So for one atom there is a two vibrational modes. So in this case 3 plus 2 plus 2, so 7. For this 4 atomic system, in this case 3 plus 2 plus how many? For this case 2, this case 2, so 2 plus 2, so is 3 and 6, 9. Okay. So at moderate temperatures, this can only the vibration mode this middle. Okay, because they can vibrate at moderate temperatures. Okay, the system is not rigid; it's loosely connected. Okay, but in this case, system is rigid. It's diatomic case. So there are the boundaries. So there are the rigids. Okay. In this case, the moderate in the middles, if there is a molecule atoms, so then they can vibrate. Okay, at moderate temperature also. So that's why in this case you can consider translational, rotational plus vibrational. Only this. The vibrational mode only this atom. Okay. So for this atom is 2. So that's a 3 plus 2 plus 2 is 7. In this case 9 for 4 atomic system. Right, it's clear now? Any further question?
Yes, sir.
Okay. So now we are going to mixing of these two system. Okay. So let's consider a gas mixer. Yeah. So let's consider a gas mixer of let's say N1 mole of gas with degree of freedom F1 and another and N2 mole of gas. So mixture of both. Okay, so N1 mole of gas with degree of freedom F1 and N2 mole of gas with degree of freedom F2, right? So then what is the gamma for this system, this gas mixer? So now question is, what is the gamma? So that means the ratio of this Cp by Cv, or maybe, okay, so what is the degree of freedom of this gas mixer? Can you tell me how to calculate this? What is the degree of freedom of this gas mixer? So the mixing of two gas. Okay, so one is F1, another is F1 degree of freedom, another is F2 degree of freedom. Okay, and we mix this, and we calculate. We like to calculate what is the degree of freedom of this gas mixer. Okay, so can you tell me how to calculate this? Okay, so let's do it quickly. So first we calculate the total energy of the system. Okay. So first we calculate the total internal energy of the system. Total internal energy of the system is E. So it's half. So there is a N1 moles, right? So that means half RT into N1 with F1 degree of freedom, right? So F1 degree of freedom, each degree of freedom can carry the same thing. So it's follow the equivalence theorem. Okay, so F1 plus into F2. So it's clear now. So F1 degrees of freedom, and you know that from equivalence of theorem, F1 degree of freedom, if the contributor to the total energy is F1 by 2 kBT, right? But now in this case, the N1 mole, right? So then F1 by 2 N1 into mole, that means Na. So N1 times Na, 1 mole of Na, number of molecules, then Na times Na kBT, right? So this is F1 by 2 RT into N1. Or you can write this N1 and NAKB each R and T. Right. So this is for the system 1 and this is for the system 2, and we are mixing them. Okay, the total energy is add up. Okay, because energy is addition. So it's clear? So this part I think clear, right? So now we calculate, let's say Cv. So the specific heat at constant volume is actually can be calculated by the one derivative, is del T at constant volume, right? So the volume fixed means that the number of molecules fixed, okay, because the temperature fixed. Okay, temperature and pressure fixed. Let's say PV equals to N kBT. So its temperature and pressure is fixed at fixed temperature and pressure. So volume fixed means the number of molecules fixed. Okay. So that means so when we add these two systems, let's say this is system 1 and this is system 2, and we can add. Okay, so it's a big system. So its volume just add up, the number of particles is just add up. Okay, so there is no loss. So that's why I calculate CV is just daily delta at constant volume. So then so yeah, so we calculate, then this is get that half R N1 F1 plus into F2, right? So then we know that Cp minus Cp, right? So this is actually in R. So what in is N1 plus N2. As a total system, in is N1 plus N2, and this Cp minus Cv from the for ideal gas. Okay, so when you do the thermodynamics, we calculate this thing that Cp minus Cv is actually in R. So it's the total number of moles in times R. So this is actually N1 plus N2 times Kb in a this type of thing. Okay. So then, and we know this, and yeah. While n is N1 plus N2, now you know Cp, and we calculate Cp, or we can calculate gamma. So gamma actually Cp by Cv. So this is actually from this we can divide it by Cv, divided by Cv. We get Cp by Cv minus 1 yeah, so Cp by Cv minus 1 is actually NR by Cv. So the Cp by Cv gamma, so this is NR by Cv plus 1. Okay, and if you know Cv, just put it, so 1 plus NR by Cv is half R N1 F1 into F2. So this R cancel, and you can get N1 F1 into F2, and it's 2N plus N1 F1 into F2. So this is the formula, and yeah, so now N is right 2N1 plus 2N2 plus N1 F1 into F2 by N1 F1 into F2. So the formula of gamma N1 F1 plus 2 into F2 plus 2 by N1 F1 into F2. So this is the compact formula. Okay, a mixing of two gas with N1 number of mole with F1 degree of freedom and N2 number of mole with F2 degree of freedom. This is the gamma. Okay, the mixture of these two. Now we calculate degree of freedom F. So this is actually 1 plus, what is this formula? Gamma and F, the degree of freedom. Can you note it? Okay, so gamma is actually 1 plus 2 by F, right? So the F is gamma minus 1 2 by gamma minus 1, right? So you know gamma and you calculate the F of this mixer, right? So it's clear? So you know gamma, right, from this. So once you calculate the gamma of this mixer, and you just put in the formula. Let's do a simple examples. So let's mix of two for gas. Okay, so let's say if one is 5 for diatomic gas, and if two is, let's say, 7 for linear triatomic. Okay, so both are at moderate temperatures, right? But in this case, the vibrational degree of freedom active. In this case, is not active. Okay, so it's so then we can calculate gamma. So let's say 1 mole and 1 mole. Okay, so N1 1 and N2 1. So N1 1 and N2 1. Then we calculate gamma. It's 1 into F1 by 2, 7, 5 plus 2, 1 into 7 plus 2. Then N1 F1. So it's 5 plus 7. So it's 7 and 16, 12. So it's actually charity. Right. So once you know gamma, and we calculate F, then 2 by charity minus 1, 6. Right. So any questions about? Hello. Yeah, any questions so far? Okay. Okay, so the next things I like to discuss. Okay, so yeah, so let's say given a average energy, right? So it's for kinetic theory of gases. Okay, so you know that the average kinetic energy EK using equiperson's theorem. Can you tell me what is the average kinetic energy? So this is the average. Okay, so its angular bracket is actually average. So average values of kinetic energy. What can you tell me from equiperson's theorem? One by 20 square. Why you say these things? Because okay, so let's say for monatomic gas, monatomic gas is only kinetic energy. So how many degrees of freedom? It's 3, right? So then the average energy is 3 by 2 kBT, right? So E mode half kBT. So there are 3 mode only for monatomic gas. So it's 3 by 2 kBT, right? So suppose this is given. So the average energy, let's say given is 10 to the power minus 15 joule. So this is given. Okay, and you then the ask that to calculate, let's say number density. Right. So how to calculate the number density from this equation from this given data? Let's say pressure is given. Let's say 1 atm pressure. So P is actually 1 atm. Then you calculate, right? So from this, so one thing we have to calculate this parameter, right? So there is only one parameter is T. So from this we can calculate, from the given data we calculate the T. Okay, and you know that for ideal gas PV equals to N kVT. So now we calculate N by V. This is your N, number density. This is the number density. Is N by V, and we can calculate this P by kVT. So you know P, you know T. From this we know T, and the P is given. So you calculate it, right? So this is one formula for ideal gas PV equals to N kVT. So if P given, the two parameter given, one parameter you can calculate. Okay. Right? Any question? Hello? Okay. So okay, so now we go to the things that thing we have to discuss. Yeah, so any questions so far? Hello, is there any questions so far? Those people are joining late. So any questions in the content, week content, and discussion forum, if you not understand? So I strongly suggest that if people should participate in the discussion forum and ask the question and answer the other people. So you have you know the answer, then you can reply and just participate in this. Okay, so then the way you can learn too many things. Okay. Okay, so let's go to the. Okay, so let's discuss something about the distributions. Okay, so this Maxwell distributions. Okay, so let's write down the Maxwell distributions. F of P is a P square to the power minus alpha P square. So this A is actually from the normalization factor. So what is the normalization? What is 0 to infinity? F of V dV must be 1. Then we calculate from this what is the value. So now I would like to ask that let's calculate the P to the power Q, the average in this distribution. How to calculate? So just that if PQ, F of V dV, and its limit is 0 to infinity by 0 to infinity FP dV. Right? So this is the average values. Okay. But you know this is the one because you put the constant this one, right? And in such a way that you calculate A. Right? So you calculate A in such a way that this is equals to 1. So then there is no need to write this. So this is equals to 1. Just only calculate this 0 to infinity V to the power Q F of V dV. Just only correct because you put the constant that this is goes to 1, right? So you can just calculate it. So if, let's say the calculate V to the power 4, V to the power 5, anything, you just put there and calculate. Okay. Just do the doing the sum integrations. Okay, a little bit, and you get the answers. Yeah, then okay, so let me discuss the other things related to that. Just open the notes and okay. So when we derive this formula, right? So when we derive this formula, so why this whisker comes in here? So first we calculate the velocity space. Let's say Vx, Vy, Vz. Let's say this is your velocity space Vx, Vy, and Vz. Okay. So I like to revisit the derivations in a briefly. Okay. So in a short manner. Okay. So this is your velocity space. Let's say Vx, Vy, and Vz. Okay, and you know that f of Vx on particular direction. Okay. So this is actually e to the power alpha. Let's say e to the power alpha Vx square. Alpha is a beta. Beta or a Vx square. This. So okay, so we write the specific form that e to the power minus Vx square by kbt. Right, so you do know how this formula comes into the picture, that why the distributions is in the Vx directions is e to the power minus Vx square by kbt. Okay, so there is a derivations in the notes, but you can intuitively say that there is a Boltzmann weight, right? So let's say a system, and there is some molecules. Okay, and the systems are temperature T. So now we can treat each molecule randomly, right? Separately. So there is a no collisions and there is a no attractive potential. Okay, so all are molecular random. So we can treat that each molecules, let's say velocity v. So this is the velocity vx. Okay, so is the of the each molecules. So then you can treat the other part of these systems. Okay, contains the molecular temperature T, and these molecules is connected to this heat bath. Okay, so when we discuss it later, that is actually a Boltzmann weight. So it's e to the power minus the molecular energy. Okay, I think there is some m. So and there is a 2. Okay, so why this is the molecular energy of sorry, energy of this molecule E by kBt. So this is your Boltzmann weight. Okay, so when a system connected to a heat bath T, okay, and the Boltzmann weight actually the in it's e to the power minus E by kBt. Now in this case, what is the energy of this molecule? The energy of this molecule only kinetic energy, so half m Vx square is the molecular mass, molecule mass, okay, not a molar mass. Okay, so it's small m, so half small m Vx square. So now we put that f of Vx is actually e to the power minus this formula is m Vx square by kBt. So you get this. So similarly, you calculate Vy and Vz, and then you will get that f of Vx, f of Vy, and Vz. Okay, you just multiply it because all our three motions are independent. Okay, that's why you multiply it. So that's f of Vx, f of Vy, and f of Vz. Just a minute. Some people I think waiting. Yeah. Okay, come back to the yeah. So the multiplet because all three are let's say bases. Okay, so they're independent to each other. So that's why you have this Vx, Vi, Vz. That's the multipliers. So we get this e to the power minus m by 2 kBt into Vx square, Vy square plus Vz square. right? And this will get the v square, right? So then e to the power minus m v square by 2 kbt. So now this thing is clear, right? But there is some factor. So now why this v square comes? Can anyone tell me why this v square come into the form? Hello? So from this case, let's say f of vx this, right? There is a no v square factor, vx square factor. These types of factor here is not appear here, or this is only appear here in this case. So when we write a, okay, so it appear here, right? So in this formula, when you write in terms of v, so v actually v square actually vx square plus v square plus vz square. Yeah, so it is clear. You can understand the questions. Hello. The question is clear.
Yes, sir.
Just tell me that why this v square appear here and why it does not appear here. Okay, so let's go systematically. Okay, so first we know that this f of vx, vy, vz is just multiplied because all are the velocity direction independent. So that's why we multiplied, right? So now, so this v square actually this not comes for even using a sphere. Okay. So this vx square plus vy square plus vz square is actually v square. This is always true. It's like x square plus y square plus z square goes to the spherical r square, right? So you can choose a length of this, and this is actually your r, right? And in the velocity space, so this is the position space. So this is the position space, okay. And this is the velocity space. Velocity space, right? This is the distance from this one particular point to this point. So now we are choosing a sphere because what is the mean for that? That means we consider that the distributions of velocity is isotropic. In all directions can distribute in the same way. Right? So till now we are not considered, we are only independent. So now we impose that in all three directions the velocity are distributed in the same way. Okay, so that means the isotropic. For only isotropic case, so we can include one by one, right? So first this point to this point, so first we calculate that only one directions. Okay, what is the f of vx looks like, you get this, and we calculate this vx average, right? You get a 0 because in this case the vx limit is actually minus infinity to plus infinity. Any value is positive direction or negative direction. It can be moved positive velocity directions, it can be moved negative velocity directions, right? But when you go this sphere, okay, so I will come to this. So in this case the vx actually minus infinity to plus infinity, and we calculate f of vx is 0, right? So the average velocity is 0. So then we can calculate similarly vy and vz. Now we calculate f of vx, vy, vz. This is actually because all three motions are independent, so that's why we multiplied. Now we impose that all three x's, okay, in the all three x's the velocity distribution is the same. Distribution is same, independent plus the same way distributed, right? So that's why we can case the isotropic case. So in isotropic case, then we can consider a sphere, right? And the velocity space we consider a sphere, and the radius of the sphere is v. So then this volume element dqv is actually initially dvx, dvy, dvz, right? But now we're just changing this vx, vy, vz to v, and let's say in this case v theta phi, right? Because you can choose a velocity space and there is a sphere, just like a spherical coordinate in the position space, r theta phi, in this case v theta phi. And changing this, and we get there is a Jacobi, is that v square sine square theta, right? Just a minute, some people v square sine square theta or sine theta. Okay, so just change. Okay, so you can this dvx, dy, d2b, and you can write this v square sine square theta, I think, yeah. So actually 4v square dv, yeah, 4v square dv. So from this case it comes from this v. So v square only comes from the isotopic case. So then you consider a sphere. Otherwise it's just like a f of vx, vy, f of vz, and dvx, dvy, dvz, just multiplied the three directions. Okay, so but this only comes, it is dvx, dvy, dvz into 4v square dv for isotopic case. Okay, so if the velocity distributions are not the same way in the x and y directions, let's say vx distribution and vy distributions are different way, right? Then we can write this thing. So it's only case when the we consider isotopic case and we multiply this, and you can consider a sphere, and then you can replace this dv square to this. Okay, so that's why the v square comes. So when we go into the more advanced thing, okay, so then we can discuss this more, because suppose there is a box and there is a little hole, okay, so I can calculate the distributions from this particle that throwing through the hole. Okay. So then this is not this type of distributions. Okay, so this is a more advanced thing. Okay, so if you guys are interested, so look into this. So I mainly follow the book. Okay, so it's the Blundell concept in thermal physics, right? So Blundell concept in thermal physics. So this is a very nice book. So whenever I read thermal physics, I go to these books. Okay, so I strongly recommend that if you guys are interested to more advanced thing and basic thing also, so go through this book and read the following chapters corresponding to the week contents. Okay, so yeah, so the sir also prefer this book, so I am also this. Okay, so if you are interested, so go through this book and read the chapter corresponding to the week contents if you are interested. Okay, so now the thing, yeah, so then you can calculate that this vx is 0, but when you calculate this isotopic distributions, okay, from this isotopic distributions, f of v, now come to the point, f of v is v square e to the power minus, so this v square comes from there, and e to the power minus alpha v square. So then we calculate v average and sum a, and we get a non-zero. Okay. So now we calculate that let's say for this case, okay, it's a very interesting thing. So for this case, okay, let's consider this only. Okay. So not isotopic case. Okay. So we consider the distributions. It looks like f of vx, f of vy, f of vz. It's just e to the power minus n vx square by 2 kbt into time e to the power minus same thing in times vy square and e to the power minus same, I think. Yeah. So this is, let's say, alpha vy square vz square and dvx, dvy, dvz. So I am writing in this form, and there is a no factor of So only normalizations constant, no fact. This is not a function of b. Okay, because I can write dvx dvy dt. Then we can calculate vx vy, the average values of the multiplied output. Okay, so it's a simple way to calculate that vx the same way as previous, that minus infinity to infinity vx vy, and there is a two integrations, sorry, three integrations, and all clumps up into the one. So then vx vy into e to the power minus the f. Okay, so this is the f vx vy dvz. So then f vx vy vz dvx dvy dvz and divided by, so we can calculate in a such a way that this normalization factor is goes to 1. So this is the normalization factor. Okay, so this is goes to 1. Okay, as we do it previously. Okay, so then we can calculate this and we get that this is a non-zero, but vx average is 0 and vy average 0. But vx v average, so this is 0. So just calculate. Okay, I'm not sure, so you calculate and tell me in the next sequence that this is 0 or not 0. Okay. So vx average 0, vy average 0, but when you calculate vx vy average, so it's 0 or non 0. Just simply say all of are independent. Hello. Okay, so it's easy to calculate. Okay, so this is 0, right? This is again 0 because all of are independent. So how? Because vx, so okay, so what is the vx average? It's just minus infinity to infinity vx f of vx vy vz into dvx, okay, and dvy and dvz, right? Because there are three integrations, so vx integration only dvx contribute, so this is 0. So similarly vy 0. So there are three integrations, one integrate on dvx, another integrate on dvy, and the integrate on dvz. So dvx integration 0 and dvy integration 0. So dvz integration is finite, but the whole thing is 0, right? So now you calculate on more things. Yeah. Okay, so now you want to calculate. Yeah, now let's say x equals to y. So let's say bx square. So let's calculate bx square. So it's just not 0, right? Similar for the v average, or okay, so let's say vx square. So this is actually minus infinity to infinity vx square e to the power minus m vx square over kbt, right, into dvx, and other things are the same, okay, as previous. So, and this is divided by the normalization factor. So then this goes to 1. So you can choose a such a way. So you get that this thing is not 0, right? So this is 0, but this is not 0. So once we say that px my py minus px py, right? So px average 0, py average 0. That means px average this is 0. So whole thing is 0. So this is one way you can say that there is a no correlations x and y. So that's why this term 0. So I will so in a different thing, different context, that when this term non-zero. Okay. So Let's say another things. Yeah, so this is zero means that there is a no correlation. This is zero means that there is a no correlation. That means one x movement of the velocity, the velocity x component of the velocity and y component of velocity cannot depend to each other. Okay, so both x and y, the vx and vy are independent. That's the one way we say it. So that's why we assume previously, but you can tell equationally that vx and vy are independent. So now one more things I to calculate. Okay, so let me think. Px py. Yeah. So okay. Okay, so now come back to the isotopic case. Okay, so f of v is a v square e to the power minus alpha v square. Okay, so you calculate in this case v average and you get the non-zero value, right? And the value is that actually v average is to the power of 8 kbt by pi m small. Okay, so now we calculate 1 over v average. So that's interesting. So when you calculate 1 over v average, so how to calculate 1 over v average? Similarly, that 0 to infinity, because in this case we choose v. So isotopic case. Okay, so we choose v, and the limit of the v actually you can choose a sphere. So that's why the limit of this v is 0 to infinity. So 1 over v a v square e to the power minus alpha v square dv, right? And by normalization factor we get a 1, and so once we calculate this we get a value non-zero, and this is non-zero, and this is not equals to, and this is also not equals to 1 over v average. So calculate, you know the v average, and you calculate 1 over v average, and you check that this 1 over v average is not equals to 1 by v average. So that is not true that 1 over v average means that 1 over v average. So this is not true in general. So in general, let's say a by b, and you can average the quantity of this. This is not that a average by b average. Okay, so this is not true. Right. So also calculate and we get these types of things that v average times 1 over v average, we get a 4 by pi. So that means, so this is actually the inverse speed. Okay, so the average values of inverse speed and speed, right? So you know that things that v times 1 over v average minus v average 1 over v average, right? So get a non-zero value, because this is 1. So 1 in average is 1, right? So this goes to 1. So if 1 in average, that means you get a 1. So this is 1. So that means 1 minus this value 4 by pi. So this is non-zero value, right? So that means the velocity and inverse speed. So this is not a velocity, it's speed. Okay, because v square, okay, this is form of v square, okay, a mod of v square and root. So this is a speed, so only positive value, and velocity can be positive and negative both, but velocity, the speed only positives. Actually is a form of v square. So if you say that this is not v, it's actually form of v square, because this is v square, this is v square. Okay, so that's the velocity only. This is actually called the speed, okay, or v square. So we get that the speed and the inverse speed are related to each other. Okay, so you can naively say that the speed and inverse speed are not independent. Because this, okay, so you calculate this and you get this, right? So the one way we can conclude these things, that this is not equals to 0, that means the speed and inverse speed are not independent to each other, they are related. And you know that I naively say that yeah, the speed and inverse speed are obviously related, but yeah, so the way we have said that here. So this is very naively we can prove this thing. And yeah, so any questions so far? You just calculate, this is a homework, you can just calculate and just do the integrations. Okay, I am already taking the form of the integrations, you can just do the integrations and check that this is correct or not. Okay, any questions so far? Hello.
No, sir. Understood.
Okay, so these things okay, so now the next things I like to discuss, just a minute. Okay, so once again I ask the same thing. Okay, so if the people, so some people are joining later. Okay, so if there is any questions from the week content and the questions in the discussions forum that you are not understood, or you can ask. So any questions related to that? Okay, I think there is no questions. Okay, so now go to the next things. Okay, so let's do one more examples. Let's say calculate first calculate the questions that calculate the RMS speed of into nitrogen molecule. Okay, so nitrogen into molecules at room temperature, right? So you know that the VRMS is just you get the from this distribution functions, you calculate the RMS velocity and you get that 3 kmt by pi small m. Okay, so now we know that the what is the values of m into, and similarly as before. Okay, so we get this m into, this is a molar mass, so once you calculate this molar mass we get this. So m into actually 28 gram. So just put it on the arcade thing. Okay, so and just verify that. Okay, so this is just for homework exercise. Okay, just verify that this is a get a fast so meter per second. Okay, so just verify this calculation. So it's correct or not. Okay, so this is the Maxwell distribution things is almost done. I think. Okay, so just looking. Let me think what we can discuss. So, yeah, anything you would like to discuss? Okay, you want to discuss that? Yeah, I am not understand this point. So if you discuss, then helpful. If anything these types of queries you have. Hello. Okay, so let's uh, let's go into the one of the discussions questions forum discussions forum questions that CV versus temperature curve. Yeah. So in the CV versus hydrogen gas H2 gas atom at 2000 Kelvin H2 can start to deassociate to 2H, and we know that for non-rigid diatomic gas CV actually 7R by 2. Then even after decisions of rigid diatomic gas hydrogen, how to do get CV actually 7R by 2 in the curve. Okay. So in the lectures, sir showing a graph. Just a minute. Yeah. So the CP and versus this, let's say CP and CP versus let's say temperature. So that's showing that these types of curves that at low temperatures, and then you can just go increases to high temperatures, and then go increases to high temperatures. Okay, so this is a 3R by 2, and this get a 5R by 2, and this is 7R by 2. So in this region, the temperature is small, only monatomic, only the translational digraphidom are active, and in this temperature regions, okay, so the translational plus vibrational. But let's say and then the when you increase the temperatures, the H2 this is for the H2 gas. Okay, so H2 gas start to dissociate. Okay, dissociation. Okay, then but you can think that let's say this is 2000 Kelvin. Okay, so at 2000 Kelvin and nearly about that. Okay, so this specific heat curve goes to this point. It's close to 7R by 2. So we can hypothetically say that yeah, so this actually saying that this, so this is actually just confirmations for that. So we are reached to the point 7R by 2 when this temperature increases and not dissociation start. Okay, so before the dissociation we have to calculate, and we reach that yeah, so CP goes to this point, that means this is actually 7R by 2 near, so we can hypothetically fit that this point to that. Okay, such that we can conclude that yeah, so vibrational mode also active at these temperatures. Okay, so that's the point. And you must remember that the before the dissociation. Okay, so dissociation, after the dissociation we have not calculated any specific heat, etc. So because the H2 dissociation, so 2H. Okay, so once you know the exact if you calculate exact temperature of the dissociation, if you know the pressure things, and then you calculate the exact dissociation temperatures. Okay, so there is a partial dissociation and then fully dissociation. Okay, so once you calculate, let's say 90% of this H2 dissociate into the 2H, so then they calculate the temperature, at which temperature the H2 dissociate to 2H at 90% level. Okay, let's say 1% of H2 dissociate to 2H. I want to calculate at which temperatures this 1% of H2 dissociate to 2H. So once you know this percentage, and once you know the pressure at which at what pressure we have to calculate these things, and then we get exact temperatures. Okay, so that's why we calculate the dissociation temperatures, and the things that discussed in the discussion forum asks. Okay, so even after the dissociation of the rigid diatomic hydrogen gas, how to get CV actually 7R by 2 in the curves. So after the dissociation, so we have to not discuss. So the CV actually 7R by 2 before the dissociation, okay, starts. So we can hypothetically say that this point, let's say this point, so this point is close to 7R by 2. So that's why you can say that yeah, so the vibrational mode can be active at this temperatures or near about. If pressure is given, then T we have to calculate. Yeah, any questions? Hello. Hello. Okay, so let's go into the previous things. I think one thing I have missed here. Yeah, so for degree of freedom case, when we calculate, let's say triatomic molecules, linear triatomic molecules, so degree of freedom for linear triatomic molecules. So we see that only these atoms contribute to the vibrational modes, right? So there is a at moderate temperature, even at moderate temperature, so let's say around room temperature 300 Kelvin or near close to that. Okay, so then we can only so then we can calculate this if the degree of freedom is translational 3 plus 2 plus 2 only. So this is the translational, this is the rotational, and the vibrational 2. So why 2 on for this case? For one atom, the vibrational modes it contribute to the 2 degree of freedom. Can you tell me that why this 2 degree of freedom contribute for each vibrational mode? So this comes from the vibrational mode, right? So for each vibrational modes, why 2 degree of freedom contributes? Because each translational modes there is a 1 degree of freedom contributes, and each rotational modes there is a 1 degree of freedom contributes. Because there is a 2 rotational, that's why 2. There is a 3 translational in 3 directions, that's why 3. But each vibrational modes the 2 degree of freedom contributes. Yeah, so can anyone tell? Hello. Okay, so let's discuss this. Okay, so and we know that for F degree of freedoms and the average energy is actually F by 2 kBT. So that means okay, so let's discuss the translation case. So for translation case means that only kinetic energy contributes, because the particle moves let's say moves on the x-axis. Translation, that means there is a kinetic energy, so it's half, let's say m with velocity vx, so that means half m vx square. So due to this vx square, the quadratic function, that's why we get a half kBT for only these motions. Okay, vx directions. Okay, so only motions for vx directions we get half kBT, and vy directions similarly for half m vy square we get a half kBT, right? Because this due to this quadratic functions, so this half comes from quadratic functions. Okay, so there is a quadratic in the velocity, that's why the half kBT contributes. That's why in this case also the half kBT, and similarly for the other directions, vj directions, and this. Okay, so due to this quadratic again half kBT contributes. So then we can calculate that this 3 translation, that means the 3 way the movements. Okay, and that's why that you can add this 3 quantity, you get 3 by 2 kBT, right? And this is actually f by 2 kBT for translation, right? So if translation, that is actually 3, right, from this case. So there is a no potential. Okay, now similarly for the rotational case, so when I rotate, let's say omega, angular speeds, okay, dot or cross, whatever you want, the axis. Okay, so then what is the kinetic energy? Half I omega square, right? So again this omega square, So it's the angular velocity omega, and then omega square, this omega square contribute half kbt. Okay, and there is another axis. So this is one particular axis. Okay, and let's say this is x axis, or another axis, let's say y. You can then, for this case also, the half ix, half iy, omega x, omega y square, and due to this omega y square we get a half kbt, right? So that's why two axis, so rotation possible under two axes, okay, x or y, and let's say this is actually in the z directions, okay, and the z axis, okay, and the only possible rotations on the x axis, on the y axis. So then for each half kbt, so that's why I get 2 times 2 kbt. Okay, so these two actually vibrational modes. So f vibrational, sorry, f rotational, right? And each contribute half kbt. So now comes to the vibrational case. For vibrational case, let's say the middle thing. Okay, so for vibrational case, vibration means that there is some simple harmonic motions, okay, oscillations. So let's say a spring, okay, so let's this atom, and there is some spring, and this atom, there is some spring, this atom, right? So this is a spring like, okay, so there is a spring like things you have connected. Then the energy, okay, so you see that this, the kinetic energy half these molecules, let's say this atom, okay, the kinetic energy half k x dot, okay, so vx square, and due to the spring, okay, the vibrational modes, okay, so there is a potential half k x square. So if this is x directional movement, and this is the spring constant of the spring k, then this, so there is a two modes, two quadratic modes, okay. So from this there is a half kbt, from this there is a half kbt, right? So here we only consider the simple harmonic approximations. That means the spring potential is this half k x square. So that means this is just quadratic, this is also quadratic. So that's why this comes from this quantity the half kbt comes, and from this portions the half kbt comes. Okay, so this total is 2 by 2 kbt for only one. Okay, so that's why I say that the if vibrational by 2 kbt. So each mode, vibrational modes contribute 2 degree of freedom. So in that case, only kinetic potential, kinetic energy contribute half I omega square, half I omega z square, or half vx square, vi square, vz square. But in this case, potential energy also contribute, because due to the spring potential. Okay, so that's why the vibrational modes 2 degree of freedom, and translation modes or rotational modes 1 degree of freedom. Okay, because in this case potentials come to the pictures. So this potential come into the picture, and due to this potential there is a half kbt one more, and we get a vibrational degree of freedom 2 for each mode. Okay. Understand? Any question?
Understood.
Yeah, so I think let's say you can also calculate the other systems, okay, if you given, okay, then but linear triatomic molecule in the same way, okay. So linear tetratomic molecule, let's say the 4 atom in there, so we discussed previously, right? So here I go into this. Yeah, so in this case there is a 2 modes, and each mode is a 2 degree of freedom due to the same digits, okay, and we get a 9. So I think these problems are all of things, that's all, okay, and we discussed today, and I think there is no problem to solve the assignments, okay, because I think most of the problems we discussed here, okay. So and exact form answer I think given there are on 2 problems, okay. So I think the assignment problems are not any issue, okay. So if you solving this thing. Any questions or so far? Because I think we discussed almost things that in the week contents. Anything you would like to discuss or want to tell something? Hello. Any questions over? Okay, so okay, so then I think can stop here. Yeah, I think discuss almost things that content. Okay, so let me think. Yeah. Yeah, so I think we discuss almost things that in the assignments. Okay, so okay, so if you are interested, sir, go through the reference that I am saying that the bundle concept in thermal physics. This is a very nice book, so read. I will discuss some of the problems in the next sessions from these books also, and some basic concept we discuss in different way. Okay, so yeah. So okay, so let me stop here. Okay, so if you have any questions, ask, or otherwise I'll stop the sessions from. Okay, so for today, yeah, okay, and we will meet tomorrow. Or tomorrow means the next sessions. Sessions is repeatedly weekly repeated, so every Saturday 4 to 6 p.m. So please come and ask the questions. And the main advantage to this live sessions, if you have any questions, then you can ask or directly and discuss things related to the week contents. So any questions?
No, sir.
Okay, so I think so we will stop here and we'll see in the next series. Okay. Okay. Thank you. Bye bye.